This video gives a demonstration on how to get started using the Bathtub model. Here we have Bathtub version 6.14 installed on the public computers. You can download it and put it on your own computer as well. Double clicking on the icon will open up this small window, and you can open up documentation if you like. It's got a lot of help screens and so forth. Saying OK. Bathtub works off of a Excel spreadsheet type format, and so it opens up Excel. So got a bunch of buttons here at the top. Edit buttons, run buttons, list buttons, and so forth, and we'll learn how to use some of these other buttons later. Help menu here is really good, being able to look at all the different things that are available. The documentation would look just like this. I mentioned about the documentation button before. This model was developed by the same person that started the Flux model, William Walker. So you have an index, you have a search menu, and so forth. So you can find out all this different information on how Bathtub works and how to actually, there are small tutorials in here, not video tutorials, but small instruction and directions for how to input data to the Bathtub model. We'll close that. Generally what we would do is we would open cases, different data files, by reading a case file. And the case files, when they're saved, have a extension .btb. So let's look here and try to find a case file. We're going to be using, to start with, a hypothetical case, and I've gotten this started for you already. We'll call it hypothetical case setup. This is the file that's loaded onto the Moodle site for you to get started with. And so I'm going to open that, and you can see that the model is already set up to do 3 segments and 5 tributaries. That's basically what's specified for part A of the homework assignment. We can go in here and we can edit different components of the input. One of those, the very first one that we would look at, is model selections. So if I click on that, we can see all the different kinds of models that are being used within Bathtub for doing calculations of chemical fate, both transport, advection, diffusion, and fate of the chemical. Let's say sedimentation of the chemical out of the water column. We will be in the assignment for part A computing a conservative substance, chloride, and so you have a choice of computing or not, and I've already set it to compute. Total phosphorus, we're using the Canfield and Bachmann general model for total phosphorus, and this is the one that was used for Medicine Lake. Total nitrogen, using the first order reaction model. Chlorophyll A, Jones and Bachmann, again the one that was used for the Medicine Lake. Transparency model, again the model was used for Medicine Lake. Chlorophyll A and turbidity component. Longitudinal dispersion, you can either not calculate it at all if there is no dispersion between segments, but because we will be modeling here a lake broken up into segments, there is a possibility of diffusion of the substance between those segments, so we will include dispersion. Phosphorus calibration, we're actually not doing any calibration. I thought I had already set this to none, so you should set that to none because we don't have any data to calibrate against when we're doing the hypothetical case. For the error analysis, well, you have a choice of doing model and data, model only, or data only. And of course we could do it where we're not calculating any error as well if we choose not computed. For our case, we'll look at model only. Availability factors we'll ignore. We do want to have estimated concentrations output. We don't have any observed concentrations. And then finally, we'll allow the output to be put to a Excel spreadsheet, not to a notepad or to a text box, because we'll want to be able to save the data in a Excel worksheet. I'll save this. If we say OK here, and then we can go back here and we can say save. So that saves the one change that I made to that input file. Then we can choose global variables, and this part I've left the rest of the data for the students in the class to complete. I did put in some titles here, but this will be the default. The averaging period is a full year, so we'll leave that at 1. But then you need to put in the precipitation amount, evaporation amount. We'll assume steady state conditions so that there's no storage gain or loss out of the lakes. You'll need to calculate the atmospheric loads. We do have a value for total phosphorus. We do not have a value for nitrogen. And for the conservative substance, we'll assume there's no chloride being transported from the atmosphere into the system. So this global variable, set of global variables, applies to all segments. All right, so what we're doing here with Bathtub is we're doing a over the year averaging. If our simulation applied only to the summer period, or let's say from spring until late fall, then it would be in, let's say, a 9-month period. And that would be fine. But in our case here, we'll assume a full year simulation. So the conditions that we put in here for precipitation, evaporation are average for the entire year. Coefficient of variation can be put in here, and I've asked in the assignment that you just, everywhere where there is an input, either precip, evaporation, chemical concentration, and so forth, you put in a coefficient of variation for all of those variables of 0.1 or 10%. So we'll just keep that uniformly 0.1 throughout, mainly because I do not have any estimates for this hypothetical case as to what the coefficient of variation value should be. But if you were putting in real data, monitored data, let's say from precipitation, evaporation, you'd actually have some way of quantifying that variability. Because obviously if I'm doing a full year average, if I had 5 years worth of data, I would have an average for the 5 years, and then I'd have a coefficient of variation for the 5 years. And that coefficient of variation value would go into that column 4CV. Same thing with the chemistry. Load values that you'd have or flow values that you'd have from the flux model would, the coefficient of variation from that model would go into that column for coefficient of variation. Okay. Then the next step is to fill in the segments. I've already set it up, so you got 3 segments. You can rename these. So if I go to the first one, instead of saying segment name 1, I could put in Lake 1 or whatever you want to call those different segments. That segment flows into segment 2 because these are in series, or I'll assume that they're in series. So segment 1 flows into segment 2 flows into segment 3, and segment 3 just basically outflows into outflow river. So you can see here, well, I got an error there because I need to fill in the information about this lake. So I need to put some values in here for segment 1, and then I can do segment 2 and so forth. So this information was given in the table that's given in the assignment. And so you put in the surface area, the mean depth, the length of the lake. Mixing depth is, I don't have real numbers for that, but the model uses a regression parameter. So for instance, if I put in here 5 square kilometers, mixing depth of 4 meter average, length of 1 kilometer, it uses a calibration equation or regression equation to calculate estimated mixing depth. So you could put this 3.9 in right there, and the coefficient of variation of 0.12. Now, the user's manual says you could just leave this as 0, but when I've tried to do that, I get an error. So it's best just to go ahead and take this number and put it in. We'll assume the hypolimnetic thickness is 0 for our simulations here. It won't be the case for our real-life situation that we'll do in this part B of the assignment. For the hypothetical case, we'll have no observed water quality data. That's what we put in here. Calibration factors should just be left alone, because it should you really should be an expert to use Bathtub before you do anything with calibration factors. Then the internal load goes in here. We've assumed no internal loading from the conservative substance, chloride in our case. But for total phosphorus, we need to put in a number. And so that number is put in as milligrams per square meter per day. That's milligrams per square meter of the lake per day. The only internal load we're considering in this assignment is the internal load from the decay of the curly pondweed. And I've given you information on the area of the lake that's got curly pondweed. I've given you the mass per unit area of the curly pondweed and also the phosphorus content of that. So you should be able to calculate the total mass of curly pondweed that's generated each year. That mass would then be divided by the area of the total lake to give you milligrams per square meter per day. Remember, the mass of curly pondweed is for 365 days for 1 year, that is, so you'd have to divide it by 365 to get the amount of phosphorus generated per day. Okay. The next step after that is to input the information for tributaries. I've got I've got areas here for 5 tributaries. And so you can, again, call these anything you want to call them. So you can change the titles if you want. And here, this would be the segment that tributary runs into. And in the assignment, I've indicated that tributary 1 and there are 2 tributaries that enter into segment 1, 1 tributary that enters into segment 2, and then a 3rd tributary that enters into, or the 4th tributary enters into segment 3. There's 1 more tributary. The 5th tributary is actually a wastewater treatment plant, and that one enters into segment 3. So because this is a hypothetical case, we do not actually have monitored data for anything except for the wastewater treatment plant. So for tributary 1, we have to come in here and tell it what area of the tributary 1 watershed in square kilometers is composed of different land uses. And we've indicated that there are 6 different land uses, and the names, we call them land use 1, land use 2. You can change those to anything you want. I'll show you where you would do that. And so you put those areas in. Those areas were given in the assignment. Let's go back now, and so basically what you do is do this for each of the tributaries, tributary 1 through tributary 5, and then the model would be set up. But before we do that, we need to define what each of those land uses is doing. So for land use 1, again, I could call it anything I want. Let's say I call this row crops. So that'll be the name that then is assigned to that particular land use for that, right? So I have up to 8 different land uses that I can define. I'm not sure, maybe you could add another one, but we don't need to have another one in this case. We only have to have, we only have 6 land uses anyhow. The runoff associated with row crops and the other 5 land uses was given in the table, so you can decorate this with that information. The runoff is in meters per year, and then the coefficient of variation I said should be 10%. Total phosphorus and total nitrogen come from a table 12 that's given in the reference Lin et al., which I've posted with the data. Be careful, because the model wants to have input in micrograms per liter, and the micrograms per liter, whereas the table 12 gives the data in milligrams per cubic meter. So you just need to be careful about that to make sure that your phosphorus concentrations are given correctly. All right, I said that backwards, didn't I? The table 12 gives the data in milligrams per liter, and you want it in milligrams per cubic meter. A milligram per cubic meter is the same thing as a part per billion. So you just need to be careful. Basically, the milligram per liter numbers have to be multiplied by 1,000. I've indicated in the assignment that the orthophosphorus value should be 50% of the total phosphorus, and the inorganic nitrogen should be 50% of the total nitrogen values that you put in here. And then lastly, I've given you what the values of the conservative substance concentration is. So that would go in here. Also, you can just put it in as a number, part per million or milligram per liter. That's fine. The model will treat it that way. So I would just suggest putting it in as milligrams per liter. All right, so again, each of these coefficient of variations would be equal to 0.1. So, for instance, I might put in here 1/10 of a meter per year for runoff. The total phosphorus might be 560 microgram per liter, or orthophosphorus 280, which would be half of that number. The total nitrogen might be 3,000 parts per billion, and the inorganic concentration would be inorganic nitrogen concentration would be 1,500. And let's say that the chloride is 1,000 milligrams per liter, or 1,000 parts per million. That does not have to be in parts per million or parts per billion, just, or I should say milligrams per liter. It could be just 1,000, and then you just have to recognize that that's part per million. Because it's conservative substance, there's nothing that happens to it. There's no reaction, so the units on it don't really matter. It does matter here for total phosphorus and total nitrogen, because there's equations that deal with the conversion of it to something else, and there those equations are affected by the units that you use. So you do this for all of the different land uses. So we do that for land use 1, and let's call this one forest, because that's the second one that I listed. And again, you just fill in the information for each one. So we get done with all those, and we would then have the characteristics for each of those land uses. And then what we're doing is we go back to the tributaries, and again, I could call these different names if I wanted to. I'd put in here, if I had monitored data, then I'd put information here about the flows. But if I'm using the model to calculate runoff and runoff volume and solute mass loads, then I would go to this column right here. So land uses are put here. Row crops, you'd have forest and so forth. There are 6 of the, should be 6 in total. And I just put in the areas, and those areas were given you in square kilometers for each of the tributaries, and just fill those in. When it is just non-point source pollution, as with the watershed 1, tributary 1, tributary 2, tributary 3, and tributary 4 are all just non-point source pollution sources. We put in here, we choose, instead of monitored inflow, we choose non-point inflow. So what it expects then is it's going to get information from this table here. for calculating that non-point source pollution input. Okay, again, tributary 1 goes into a segment. In this case, it's just listed as segment 1, if that's actually the one that was specified in the assignment. For what I would do here is I call tributary 5 is the one associated with wastewater treatment plant. It goes into segment 3, and there we do have monitored flow. The outflow from the wastewater treatment plant is 4 million gallons per day. We have to convert that to million cubic meters per year. Area doesn't really mean anything as far as the wastewater treatment plant is concerned, so we can just leave that as 0. But the annual flow rate is just 4 million 4 million gallons per day converted to million cubic meters per year. Total phosphorus was given, total nitrogen was given for the concentrations in the wastewater, and also the chloride concentration was given as well. And again, the orthophosphorus would be 50% of the total phosphorus, and the inorganic nitrogen would be 50% of the total nitrogen. Again, you'd use 10% for the coefficient of variation values. Once you've got all those in, then we will save the file, and here I'm going to call it something different because I'm going to just put in here video trial, and it saved that for me. Then what I can do is I've got the export coefficient defined, I've got the tributaries defined, I've got the segments, I've got the global variables, I've got the model selection. Everything should be ready at this point. We're not using channels. You'd have to look up. I can explain to you how channels would be used, but I won't do that at this point in time. So at that point we'd be ready to run the model. And so we just choose to run. Of course, if I do that here, I should get an error. And the warning says, while the inflow concentration for the non-point source flow for tributary 1 total phosphorus is less than or equal to 0. So that's just a warning. And we'll get some errors because segment 2 hasn't been defined and segment 3 hasn't been defined, and all these things are broken because I don't have all the information in there. That's for you to input. What I'll do here is I'll read a file, and I'm going to provide you with this file, by the way, the file for Medicine Lake. And this is the Medicine Lake bathtub input. There are 11 tributaries, assume one segment. So model selection is here. In that case, we weren't computing the conservative substance. Global variables. Segments. There's only one segment in our case. Morphology is here. We did have a limnetic thickness in that case. We have observed water quality data. We do have an internal load, but in this case the internal load hasn't been added in yet. Remember in my lecture I talked about the fact that for 2006 there was no internal load, and so that could be left as 0. But with it being 0, it would not simulate 2004 or 2007 conditions very well. Tributary information is given here. In this case, all the tributaries were monitored, so we had monitor inflow from those tributaries. And a flux model was used to calculate all these quantities. Land uses were not used in this case because we had monitored input. We weren't trying to calculate the inflow mass and inflow of water. We were instead using monitored data for input. That was Ridgedale Creek, Plymouth Creek, 18th Avenue, and so forth. I'll provide you with this file so that you'll be able to see it. Actually, I'll load it up onto the website or on the Moodle site, so you'll be able to download this and see how things are structured. Got the tributary information in, and the segment information. There are no export coefficients in this case because we're not trying to calculate inputs. We actually have monitored inputs. No wastewater treatment plant in this case. So once we've got all that in, we can just say run, and the model runs very quickly. You get total phosphorus 46, chloride 21, and satiety disk 1.9. These numbers are very close to what was observed. And with that, we can plot the result, and it'll come up and it'll plot a default, in this case, the total phosphorus. But we can plot other things such as total nitrogen. We can plot satiety disk, depth. And in the assignment, I've asked you to also plot, or not necessarily plot, but calculate the Carlson TSI. And there are 3 TSI values. There's one based on phosphorus, one based on chloride, and one based on satiety. And from this, you're able to determine the trophic status of the lake. And I've provided a document from Wikipedia that explains how to interpret the TSI value in terms of the eutrophic status of a lake. I've asked you to interpret that for these 3 segments. Now in this case there's only one segment, so we only have one output for the phosphorus and so forth. Here, I'll go back up to the phosphorus line. You see the mean value predicted by the model, and of course there's quite a bit of variation, and the variation is because of uncertainty in the input, the coefficient of variation in the input. The adjusted or the area weighted mean is the same as the value for the single segment because there is only one segment. But in the assignment you'll have 3 segments, and so the area weighted mean would be the mean weighted based on the area of each of the segments. We can also output, we can list the inputs, we can list the segment network, we can list the hydraulics. One of the things I've asked you to do is to look at the mass balances, both for the water and for the solutes. So here you can look at them by segment, you can look at them overall. I'll just list this for you. And it comes out in the form of an Excel spreadsheet. So you'd have all the information. This is overall. So you've got the inputs for each of the tributaries, Ridgedale Creek, the area of Ridgedale Creek, the inflow. This is all input data. The variability that's associated with the coefficient of variation is there, 0.1. So, and then the runoff was 0.27. The tributary inflow to the lake is given on this line. The total inflow, which includes precipitation, is on that line. The effective outflow, there's only one segment, so there's only one outflow point. So this would be the output of water and chemical, and then total outflow is given here. Actually, this is all just the water part, not chemical part. And then the next line gives us the information for the total phosphorus, and we should have one also for, well, I guess in this case we didn't ask for the output to be given for the nitrogen, but if we wanted it for nitrogen we could output that. And if we wanted it for the conservative solute, we weren't calculating it in this case, but if we want it for the conservative solute, we could get it for the conservative solute as well. It's just given in the preferences where you can choose those. Okay, so that explains, I think, pretty much what I was interested in showing to you. I'm sure there will be some questions about how to use the model. I hope that I've shown you main features that will be necessary to complete the part A of the assignment. With that, that ends this video.